But nobody sent me an email, so unless you did and I didn't see it, which is, that could be true, but I don't think that's true. So I'm sorry that I didn't get the homework answers up until, I don't know, whatever time it was. I think I was here already. But anyway, I am open for questions on homework. That was my first thing before we start new content. If you have questions, here's the list of all of the stuff that we've done. Do you have questions? Are there things that you want to talk about? Or, I get it. And if you were curious about the answers to those 2 rotational equilibrium problems from yesterday, I have not written those solutions up yet. I apologize. If I get a chance to, my goal is to get it done today, like 7th period, but I've got a lot of physics kids coming in to get help. So we'll, fingers crossed. Do you have questions on homework? Is there anything I can help you with right now? If not, I've got plenty of other stuff to do, and we can talk about this stuff later too. I'm just
about it later.
okay. I mean, I'm not going to promise you like an infinite amount of time later, but I can talk about it a little bit later if you need to, or you can come in and get help if you want. Yeah. Okay. So should we move on to new stuff today? Fantastic. That was not very enthusiastic, Courtney.
Yes.
This is going to be a great day.
Still my unit.
It's still your unit, friend. Here's your question. This is your question to start the day. A rotating carousel has one child sitting on a horse near the outer edge and another child sitting on a lion halfway out from the center. My question for you is who's going faster? Once you've answered question A, then answer question B. Like if you were on a race, right? Lined up. Who wins? All right. Are you ready?
Yeah.
All right. So part A, question A. What did you say? Who's going faster? The kid on the horse that's sitting near the outer edge, or the kid on the lion seated halfway in? Horse?
Yeah.
Why do you say the horse wins? Or excuse me, the horse is going faster? It's the same time, but a longer distance? Is that what you said? What do you mean same time?
Because they go around.
So if I draw my carousel, so here's the center of the carousel. And so I've got the horse is right here and the lion is here. So the horse and the lion, you say same time. They're going all around together, right? But you're saying that it goes a longer distance? Is that okay? Do you guys all agree that the horse goes faster?
Yeah.
Because like if you draw a circle like through the lion and through the horse, and
Yeah.
then you like rolled them out in a straight line.
Yep. Yep.
And because they're going the same, they're going the same speed, or you just said same time. Because the longer distance, it would have to be going faster to make up more distance in the same time.
What do you guys think?
Yeah.
Does that sound okay? So the horses, the distance, if you rolled it out, would be further. And since it's further in the same time, it's got to be going faster. Yeah? Were you happy with that answer, Cole? You seemed unhappy with it a minute ago.
Well, it's just not there. It can refer to either.
Which is where we're going today, right? Yeah. Who wins the race?
It's the lion. It's fast.
Wait. Hold on. You told me the horse. Well, no, yeah, you said the horse is going faster.
The horse comes alive and then runs on the carousel.
Oh, so we're thinking like old Mary Poppins. Is that what you're like? That where you're? You guys remember that, right? When they're on the carousel and they start. No. So you go back and watch that movie again. It's a great one. Who wins? What did you say?
No.
Who actually wins? Rudy, what did you say?
Nobody.
Nobody. Why?
They both go with the same angle per second.
So they go the same distance. They both do one revolution in the same time, right? So some of you are getting this. Some of you are like, what? Most of you are like, oh, there's got to be some other way to describe this, right? What do you want to call it? You said it out loud. No.
I said
RPM.
Kind of, yeah.
angular speed.
Angular speed. Yeah. That's what I said. All right. In your notes, my friends, we are going to relive, 2 or 3 days in one. Here we go. Ready? We're going to turn on fast track. Easiest way that I know to do this is to relive the past first. So we're going to make ourselves a little chart. And on the the left-hand side of the chart, we're going to put all the stuff we're familiar with. We're going to write down the translational kinematics information. Translational is the fancy term for like that one-dimensional, that linear motion, that stuff that we're used to, the stuff that we've been doing all year long. Okay? When we first started talking about kinematics, remember kinematics is just trying to document the motion. The first thing we talked about was displacement. I'm actually going to, let me see. Change this up because that's what I do. I'm sorry for all of you that get mad at me when I change stuff. I'm going to write displacement here. Are you mad at me already? I'm sorry. Yeah. This is what happens when I do notes from memory. Sorry about that. It happens. I'm just trying to make it pretty. Is that okay? There you go. Displacement. It'll work. All right. Translational displacement is marked with a delta X, right? Or a D, depending on what we want to talk about. It really is, I'm just making a chart here. I'm just filling in the left-hand side right now, okay? It's a change in position. Okay? And it's measured in what? Meters. Yeah. I'm going to put all my units in little brackets like that just so I can kind of keep track of them. Okay. Translational motion, we've got displacement. This is like the easy peasy stuff. That's when we're moving a straight line. When we're not moving a straight line, when we're moving in a circle, though, that's the rotational business, right? So here we go. We're going to do rotational over here. Okay. Instead of marking it with a delta X, now we're measuring a displacement as an angle. And so we're going to use what letter? Anybody? Theta. Delta theta. Okay? It is a measure of displacement just like our delta X is, but it's a measure as an angle. We remember that the angles are measured so that it's positive is counterclockwise and negative is clockwise. We said that a couple days ago, but just so we've got it all documented here. Okay? And it's measured from the x-axis. And the units that we measure in when we're talking about rotational motion, we're going to measure in radians. I love the woohoo. That was a really happy thing. Now, sometimes when I teach this, I get a lot of groans or a lot of oh no's or whatever. So I need to know really quickly how we all feel about radians. And I want you to be honest, because I know that some people are like, love them and see the beauty of them. Is there anybody out there that's feeling like, radians are not my deal and I just need like a little refresher? Is that a yeah from anybody? Yeah, thank you. All right, let me give you the short version of radians, okay? Because I think it's important. Mostly because if you have not been introduced to it well, then it just seems really scary. Radians are super not scary, like decidedly not scary. But like I said, and I'm speaking from experience because I had a really, really bad like pre-calc trig teacher when I was in high school. And so I didn't understand it until I got into like Calc 2. And then I finally got it, I'm like, oh, this is dumb. Like, why have I been afraid of this for the last 3 years? Like, that's silly. So that I'm just looking out for all my friends who may have that kind of experience in their life. All right. And I'm not saying that you had a bad Calc 2 pre-calc teacher. I'm just saying maybe you were sick that day or something. All right. So what is a radian? A radian is just a ratio. That's all it is. So the way that I used to teach this when I taught how radians worked was using little, do you remember, those candies that are called Smarties? The little circle candies? So we did this with Smarties. Did you guys do this? Have you done this before or no? Okay, so I'm going to just tell you the story of Smarties and how they work and how you might learn this with Smarties. So you get your little Smarties and you get this little axis, and I'm just going to line up, I don't know, 3 Smarties in a row. Okay, so go ahead and draw this picture if you want because it's kind of fun. 1, 2, 3 Smarties. Okay, and then I'm going to make a little circle, a little arc that's 3 Smarties tall. 3 Smarties around. So it goes like this. 1, that's 2, 3. That's cute. You're like, okay, great. That's fun. Now, let's say I want to do another one. Let's make one that's 6 wide, right? So I've got 1, 2, 3. So I'm going to go 4, 5, 6. And now I'm going to go, oops, come on, stylus. You're with me. 1, 2, 3, 4, 5, 6. We okay? Let's do one with, I don't know, 10? Woo, that's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do you notice? And this isn't perfect, but what do you notice?
Colorful.
It's colorful, yes. You're like captain of stating the obvious. What do you notice, Jacob? You're like acting it out there.
Could like draw a line and connect and all these like
We absolutely could. Oops, that was not successful. There we go. And this right here is 1 radian. A radian is just defined as the ratio between the radius and the arc length, where the radius and the arc length equals 1, right? The ratio between them. That's all it is. That's all it is. So that's what we do. So we do it like 4 times and we see, oh my gosh, it's the same darn thing. And then, so now, like if I'm doing the purple one, I can count. So I've got 1, 2, 3. 3 Smarties equals 1 radian. And then you can like move them around, doop, 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 keep going. And then if you count all those Smarties, so let me like draw that picture. So where are my little purple Smarties? So here we go. So we're going to go like this. And this is not going to work out perfectly because, you know, I'm just kind of drawing and all of my Smarties are not the same size. But if you do this with actual Smarties on an actual line that's an actual half circle, and we count these up, how many 3s am I going to get? How many radians are in 180 degrees, friends? He's going to keep reciting forever. It's going to be about pi of them. So it's going to be just a little over 6, or excuse me, just a little over 9. Does that make sense? And then if you figure out this one and you figure out this one, then holy cow, if you keep doing that, if you have a few different pieces of data, then you can see that the number of this in this arc and in this arc and in this arc, it's just a little bit over 3 every time. And then if you get more Smarties, because you have to like get like more bags of Smarties to do this, then you can go all the way around. And then if you count them up, you get 2 pi of them, right? You get 2 pi radians worth. Is that kind of making sense? It's just a ratio. That's all it is. And the reason I want you to know that is because I don't want you to be scared of it. The things you need to know about pi, because, or not pi, excuse me, about radians. Let's write this down. It's a ratio between arc length and radius. Okay. The fancy number pi is equal to, or I should say pi radians, happens to be 180 degrees in our degree brain. Okay? If you go all the way around, you get 2 pi's. That's all it is. Okay? So I just want you to be aware of that so that you don't always go back and say, oh, I've got to do degrees, because we do degrees sometimes, like we do degrees when we're doing our inclined planes or when we're doing our pendulum, stuff like that. But whenever we start talking about this rotational motion stuff, we don't care what that degree angle is. We care about it in terms of radians. And you can talk about it in terms of pi radians or however many radians, but then when you're starting to cancel things, those radians just go poof, go away, which makes things really interesting in just a minute. Life is good so far? How are we doing?
Yeah.
You good? All right. Let's do some more. After we did displacement, what was the next thing we did? Displacement over time is velocity. Yes. So here we go. We'll do that one next. So translational velocity, easy, no problem. Marks with a V is equal to change in position over time. You can also write that as d over t. I cannot remember for the life of me whether we use d or delta x in this class because I do it differently in every class, and that's on me. Okay, do we use t?
D.
We use d. Okay, let me write d
We use
then.
both.
Okay, whatever.
D.
No, we use D.
Okay, stop fighting. It doesn't matter. This velocity is true for a straight line. You can also talk about it as the tangential velocity when something's moving in a circle, right? I'm going to explain it in just a minute. Just write it down, then we'll explain it. When object moves in a circle. What does tangential mean? Tangent. Do you know what that means? Like what, when you were not doing like sine over cosine stuff, not that. But when you like first started defining tangent when you were in geometry class, the tangent was what? Somebody tell me.
It's a line.
A line that hits the outside of the circle continues on.
Yeah?
Exactly one.
At exactly one spot, right? And that means if it hits it in exactly one spot, you wrote this proof. I know you did it in geometry. You proved that the tangent is what to the radius? Always perpendicular to the radius. Yeah, yeah. So the game is, friends, and we're going to do a problem like this in just a second here, that if you've got an object and it's going around in a circle, hi, how'd it go? Awesome, thanks. All right. Madeline, we're doing this in physics too. Tangential velocity, right? Yeah, it's exciting. Yeah, sorry, just a little cross curricular, except it's all physics, you know. This velocity goes in that direction, okay? It's the velocity that is tangent to the radius of the circle. And we'll talk a little bit more about what that means in just a minute once we write down the other alternative, okay? So this is well understood. You've understood this since middle school, maybe since elementary school. I don't know, something like that. That's velocity, but that's velocity when we're talking about linear translational motion. When we start talking about rotational, and rotational and angular, by the way, are synonymous. So I'm going to say rotational and angular here. Just to like, you know, throw more words in your face. You're welcome. Yeah. Angular velocity. Eventually, you'll be familiar with, well, many of these letters up here. Angular velocity is not marked with a Roman letter. It's also marked with a Greek letter, just like theta is. Angular velocity is marked with, anybody know? We met it before. it before. Remember? And I told you, just wait a few days and we'll do it again. Here it comes. Omega is, guys, please. Omega is angular velocity. We'll just write down that this is omega so we don't forget. Because it's not a curly W and it's not a W, it's an omega. Okay? I just want to make that very clear. Did you have a question?
No.
Okay. Just like translational velocity is change in position over time or displacement over time, same thing happens here. Angular velocity or rotational velocity is equal to change in position over time. What is the change in position when we're talking about rotation? Change in theta. Okay. Oh, I guess we forgot to write down the units over here, but we knew them. What were the units for the translational velocity? Meters per second. I just got ahead of myself. I got super excited. Okay, what are the units for angular velocity going to be? Radians per second. Okay. Now, I'm trying to set up. Yeah, we're totally ready for this. Do you remember when we talked about omega before?
Yes.
What was the context? With period and frequency, right? So I want to, this is just kind of a little aside here. Do you remember what we said? We said that F was equal to 2 pi omega. Is that okay? Did I say that right? Is that right? That's right.
Yeah.
Omega is 2 pi F. No, we said it backwards. Sorry. Right? Yeah, that makes more sense to me. What's 2 pi? A circle. It's 1 revolution. Do you see what's going on here? So this is 1 revolution. And what's the frequency? 1 over the period, right? There is not a lot of concentration going on back here. And if you guys need to move so that you're paying attention, then please do. Okay? I'm looking at all 3 of you. Okay. So frequency is 1 over period, right? So really, what I said by this when I said, trust me, we'll get there, is 2 pi over t. Yeah? Which is the distance for 1 circle or 1 revolution. And t is the time for 1 revolution. Right? So it's legitimate, it's real, and this is how it all relates. But this is where it really comes from. That's where it really initiates from. Okay? Oh. Okay, and I'm going to pause there for a second, but I want to make sure we're okay. So I'm going to go back to the carousel race here. This is the one we had before. We said this before, but we're going to say it in a little bit more specific way right now. So I said who's going faster, and now I'm going to ask in 2 different ways who has the greater linear speed and who has the greater angular speed. I'm just going to give you a second to talk with your table mates about this. You got this.
Miss Carolyn, we literally just got done with this. No, we're doing this in pre-calc right now.
Perfect! That's awesome.
The time's up.
But now you're going to learn it, right? So if you didn't get it before, now you will. You see what I'm saying?
It's helpful, yeah.
Well, good. Good. It's perfect then. All right, so what's the right answer? Who has the greater linear speed? The horse. And this is exactly what you said before, right? We just didn't have the vocabulary to say it. Friends, I feel like there's a lot of lack of paying attention going on over here too. And if you know this, that's fine, but please don't distract from what we're doing. Okay? So the horse has a greater linear speed because it's traveling more distance in the same amount of time. But who has a greater angular speed?
Nobody.
they have the same angular speed, don't they? They're going the same distance in the same time when we talk about the angle that it travels
Is
through.
that because it's like centered around the center, and then the linear one, the linear one is like about around the outside?
Yeah, that's exactly right. So if you go back, I mean, no, Isaac, I want to make sure this makes sense to you, right? So if you have the lion here and the horse here, and then maybe it doesn't go all the way around. Maybe they, like the carousel operator, like there's something wrong, they need to stop it right away, right? So if they start out here and then they go here, right? And so the lion is right here and the horse is right here. This is exactly what we drew with the Smarties a minute ago.
Yeah.
So they sweep out the same angle in the same amount of time. So even though the horse has gone further in a translational sense, which is what we are super used to, in terms of angular displacement, same. Same displacement in the same time, so the same velocity. Yeah. Is that okay? Does that help?
Yeah.
Okay, cool. All right. Let me make sure there wasn't one more that I wanted to do. Yes, we're into one more problem. It's actually 3 problems. They're just kind of some thinker problems to make sure that this stuff is making sense to you before we move too fast. So, a rigid body is rotating counterclockwise. What does rigid mean?
Stiff, hard.
Stiff, right? So it means that this thing, as it's rotating, is not going to change shape. And it's a specific term that I want to make sure you understand. If it's rigid, that means it's not going to change shape, which means that the lion and the horse are going to move. They're going to sweep out the same angle in the same time. That's what it means when it says rigid. So a rigid body is rotating counterclockwise about a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position of the rigid body. Just to make sure that we're feeling good about our radians, which of the sets can occur only if the rigid body rotates through more than 180 degrees? Take a look at that.
Bless you.
Good and talk to you. C. Why do you say C? Rihanna, what did you say?
It's the only difference greater than pi.
Only difference greater than pi. So 5 minus 1 is 4, and 4 is greater than pi, and we have to have something bigger than pi. Okay, that seems reasonable. All right. Suppose that the change in angular position for each pair of values occurred in 1 second. Which one represents the lowest angular speed? Check with your table mates, make sure they agree. What do we say? B. Why do you say B? Yeah. This stuff, friends, is not super scary. You just got to make sure that you're thinking about it in terms of the quantities that we're talking about, right? So we're doing omega is equal to delta theta over t. If the time is all the same, then the one with the smallest delta theta is going to be the one with the smallest angular speed, right? Yeah. Okay, there's one more of these questions, but we need to write down something before we do that. We just did position or displacement. We just did velocity. And what comes next?
Acceleration.
Woo! You don't like acceleration?
No.
Why?
I always mess it up.
Oh, we're gonna get it. We're gonna get it this time. I believe in you. All right. Let's do the translational stuff because we understand that. What does it mean to accelerate translationally? Acceleration is equal to delta V over T, right? There's nothing secret or fancy about that. Like, that's what it is. It is what it is. All right. Angular acceleration. It's like you guys are like anticipating something evil and terrible. This is not. Friends, because look, I mean, these are almost exactly the same, right? These are almost exactly the same. So you think this one's going to be pretty much exactly the same, right? It's going to be the same stuff. All we're doing is using different letters. That's really all it is. Angular acceleration is marked with alpha. Alpha, the first letter in the Greek alphabet. It's also the one that sounds most like the letter A, right? Alpha is for acceleration, just like A is for acceleration. Yeah? It's easy peasy, you got this. Now, whether or not you like the letter alpha, we can do this, right? What is it going to be? Translational is change in velocity over time. What's the rotational acceleration going to look like? Yeah, this is not hard. Delta omega over t. Boom, done. Okay? Sometimes called angular acceleration, sometimes called rotational acceleration. Either way, there it is. Units. We didn't write the units down for regular acceleration, but I'll do that real quick. Meters per second squared. Gotcha. All right, you help me out with this one. Oops, why did my T not actually... Radians. That was fun. How are we doing? We okay? Everybody's still smiling. All right. There was one more little quick quiz thing that I wanted to give to you. There was the first one. Here, let me just make these smaller so you can, or zoom it up. Zoom it up. And there's the last one. There it is. Let's see if I can fit it all on one page. All right. It says, consider again, I don't know who wrote that, the pairs of angular positions above. If the object starts from rest at the initial angular position and moves clockwise with a constant angular acceleration and arrives at the final angular position with the same angular speeds, in all three cases, for which choice is the angular acceleration the highest? What? Read that and think about it for a minute. It is a lot of words. I'll let you read it. Not in my voice this time, but in yours. Let's do it. All right, what you got? Ken, did you say B? Can you tell us why?
Well, they all get to the same velocity at the end, so they all have the same change in omega. So then the one that gets there in the shortest amount of time, which would be the shortest distance, have the fastest acceleration.
Do you guys catch that?
Yeah.
Can I say kind of what you said one more time?
Yeah.
So you said, oops, it's on free, so you can't see the brilliance that I wrote. No, not really. I just said omega initial to omega final. They all start out with how fast? Zero. And they all end with the same. Whatever that velocity is, they all end with the same speed, right? Okay? So they all have the same change in omega. So alpha is equal to delta omega over t. They all have the same change in omega, right? Do we know about the time that it takes? We don't. There's no time up there. So Kian, say it one more time. So how did you figure out the time situation?
Well, the one with the shortest distance would be the shortest time.
Does that make sense? Yeah. So shortest distance?
He's like that.
Poetry.
We can say it's equal to distance over time squared and say that all the times are the same. So,
Yeah. It's a nice way to say it too. Love it. All right. Do one more like this, and then we're going to write one more thing down. Woo! Got so much to do. Graphing number 1. You thought you were done, but you're not. We love to graph. I feel like this is like my Mary Poppins day today. Do you remember that? Do you guys remember that old Mary Poppins movie?
Yeah.
Yeah, that I love to laugh and they dance on the ceiling or whatever. Yeah, that's what this, except a graph instead of laugh. All right, you're welcome. All right, here we go. Angular velocity versus time graph. Okay. Angular acceleration versus time graph. It says, sketch an angular acceleration versus time graph given the angular velocity versus time graph shown. Now, this is one of these interesting opportunities. I'm actually going to click away from this for a second so that you listen to me. Haha. Okay. Remember I told you yesterday we were talking about whether or not we're going to have a final, whether or not we're going to have to review all this stuff because the AP exam is coming up. And I said, oh yeah, and it's all going to come back and we're all going to like review this, right?
Right.
This is like built-in review. Because 3 months ago, 5 months ago, I don't remember what it was, we did this stuff. Remember we had those like laminated graphs and we put them out and we like put them together? And then I gave you like a displacement graph and you had to build the velocity graph. And if you had a displacement graph and you were trying to build a velocity graph, what did you have to look at? Do you remember?
Slopes.
Slopes, right? You made a little chart. You had this, it's probably on a gold piece of paper sitting in your binder somewhere, right? And then if you had the velocity versus time graph and you wanted to get to the acceleration versus time graph, you had to look at something. What was that? The slope.
Yeah.
Right? And then to go the other way, you had to look at the area under the curve. Are you with me there?
Yeah.
I know. Woo! Now, here's the thing. Here is the opportunity that you have, friends. That was all translational. That was all like 4 months ago, 5 months ago. And now, for you today, right? You have the opportunity to do the same darn thing. Friends, it's the same stuff, just with Greek letters. That's all that it is. All that it is. So, that all said, do it. Do it.
See it, guys. Draw it.
You're going from a velocity versus time graph to an acceleration versus time graph, right? And what do we look at when we're going from velocity to acceleration? Oops, whoa, that was not what I intended to open. We don't really have values on the other axis, so let's just kind of figure it out, right?
And 0.
Why don't you check, once your table agrees, why don't you check with another table? See if they agree.
I already asked you that. So we got constant and then the 0 and then the negative 3 and then 0.
It's not scary, or it shouldn't be scary. If you're feeling afraid, then let's talk so we can get yourself unafraid. Ellie Chen, do you feel like you have a graph up back there? You're working on it? Awesome. Jonathan, how are you doing? Got an answer? Do you want to get us started? Can you at least do the first bit? Like the first 2 time units? Yeah, you're exactly right. It's going to be a flat positive line because the slope of this is constant and positive, right? Constant and positive means constant and positive. All right, talk to me about the next one.
0.
The slope of this part is what? 0. And does that go? That's like, okay, yeah. So that means we're going to be here. Troop. And then the next time unit? Negative. Now, there aren't any like units on the side, right? But should it be the same? This is supposed to be flat. Sorry about that. That's not very nice. I just realized that. Yeah. Is this one going to be the same distance below? More or less? More. Like twice as much, right? Yeah. So now I'm going to like try and eyeball it, which is totally going to be wrong with something like this. Ish. And then what happens after that? 0 again. That's not too bad. We okay? You can do this. All right. In the next 2 minutes, we've got to write down the rest of what we need for today. So here we go. That was all of that. You fondly remember, this was so long ago now. We worked through and we derived, like we legitimately derived all of the kinematics equations. Do you remember that? It was kind of a painful experience, if I recall right. But we're going to write them down. Here we go. VF is equal to VI plus AT. That's the definition of acceleration. right? You also had my favorite one. D is equal to VIT. This is your favorite one too, right? Because it's the best. Yeah? And then there was that one that was squared. That was the hardest one for us to derive, but we did it. It was fantastic. I remember. Yeah? So we went through and like legitimately figured all of these out. It was great. This is all translational stuff. I want you to write the rotational equivalence. You can handle it. I know you can. I believe in you. Anytime you see a V, you're going to write an omega. Anytime you see a T, you're going to write a T. Anytime you see a D, you're going to write a theta. Anytime you see an A, you're going to write an alpha. That's all you're going to do. They're all there. Oh my gosh! All right, my friends, I'll see you tomorrow. It'll be great. If you need to check them, they're up on the board. There's homework for this, I'm sure. Take a look through it. Let me know if you need help. If you want to come in, or if you want to stay, or come in during Liberty time, whatever works. I will see you tomorrow. Henry, what's your take on tomorrow? You think we're going to have school?
I'm retired.
You're retired? If we don't have school, when are you going to check your email, friends? After 9. Yep, you got it.